Hello, sir. Morning. It's Nikomoni Kashyap from your Mechanical Engineering Department, Tezpur University. Here is the PPT PowerPoint presentation of your asking questions. For the first one, you give u equal to ax y minus b, where you give the value of a and b. We have to find how many y components are possible. For the question, here's the answer. Given u equal to ax y minus b, after putting the value of a and b, we get the value of u equal to xy minus 6x. We know that for a steady and incomplete flow, it is also valid. Fx can be any function of x, therefore it can have infinite number of solutions for y component. The simplest is fx equal to 0. So vx equal to 6y minus y square by 2. For the second question, you give the velocity field v and also the value of a in measured in meters. So we have to find the acceleration for a fluid particle at point 2, 1. Here is the solution. V equal to ui plus vj. After putting the value of u and v, we get u equal to ax to the power 4 minus a6xy square minus a to the power a into y to the power 4, where is the v equal to a4 xy cube minus 4x cube y. We know that the material acceleration equal to convective acceleration plus local acceleration, where we have to get the value of ax equal to du by dt plus u du by dx plus w dv by dz. In that, similarly, we get the value of ay and az. After du by dt equal to 0, we get du by dx equal to x cube minus 3x square 3x y square, dy by dx equal to minus 3x 2y minus y cube, and du by dz equal to 0. After putting the value of dv by dt equal to 0, we get dv by dx equal to y cube minus 3x square, also dv by dy equal to 3x square minus x cube, dv by dz equal to 0. After putting value of a, we get the ax equal to 62.5 meter per second square, ay equal to 31.25 meter per second square for incompressible flow, du by dx plus dv by dy equal to 0. So we get x cube minus 3x square 3xy square plus 3xy cube plus 3x y cube minus x cube equal to 0. Our third question is, an incompressible liquid with a negligible viscosity flows steadily through a horizontal pipe. The pipe diameter linearly varies from 4 inch to 1 inch over length of 6 feet. Develop an expression. We have to develop an expression for acceleration of fluid particle along the pipe center line. Plot the center line velocity and the acceleration versus position along the pipe if inlet center line velocity is 3 feet per second. Going towards the solution, here we get the diameter changes linearly as we get from equation. Flow in a pipe with variable diameter, we have to express for particle acceleration. I plot of velocity and acceleration value positioning along with the continuity s. Here is the basic equation of the continuity. Assumption for incomplete flow and second one is the uniform flow. We get the diameter of the pipe, this where I is the length and x is the distance. By Bernoulli's principle, we know that a1 v1 equal to a2 v2. Then we find the velocity expression from this equation. For the incomplete flow, the continuity reduced to summation over cs vector of the volume and factor of the area equal to 0, for the rate of the flow equal to Q equal to V into A equal to V pi d square by 4, but d equal to di plus d naught minus di by L, where di and d naught are the inlet and exit diameter and x is the distance along the pipe length. After calculating Vi into pi d square by 4, we get the value Vx equal to Vi by 1 plus d naught minus di, d naught by di minus 1 by L into x whole square. Some values after putting x in the equation of velocity v equal to 0, we get v equal to 0, we get 3 ft by s, where we have to find the value of v by a. We have to find the value for 0 L by 2 and L. Now we get this performing the partial differentiating. So V L by 2 equal to 7.68 by ft by s and VL equal to 48 ft by s. The acceleration of the flow is given by AP, where we get the value of AX. After the calculating AX, we get the value of AX equal to minus 2 Vi square d0 by d naught by di minus 1 by L into x d naught by di minus 1 by L plus to the power 5. Then we have the graph of the both pipe diameter, pipe length and the flow. This is the desired graph of the equation. Thank you.